Hello students, welcome to the lecture series on carboxylic acid esters, acid chlorides. We will discuss the preparation first. Now primary alcohols, they can be oxidized to your acid. So initially in the first step, they will form the aldehyde, which on further oxidation will go to the acid. Okay. Now we have previously seen that when primary alcohols, these are primary alcohols, when they are oxidized using PDC in presence of dichloromethane, they will form the aldehyde. Sorry. However, when such primary alcohols are treated with PDC, but the solvent is changed to DMF, then they form the acid. This may be due to the presence of water, some amount of water inside the DMF. Now, other oxidizing agents can be alkaline KMnO4 in presence of heat. It can be acidic KMnO4 or even the oxoacid. Nitric acid can be used for oxidizing. Here is one example in which we are oxidizing aldehyde in the presence of acidic KMnO4 to the acid. They can also be prepared as I've shown in the second procedure using a Grignard reagent. Now Grignard reagent, when it reacts with dry ice, okay, the nucleophile makes a nucleophilic attack on the electrophilic carbon, all right, and converting this sp hybridized carbon to sp2, which on acidic workup, this is our acidic workup, they will form the acid. Also alkyl nitriles, these are your alkyl nitriles, and they can be under the treatment of acid or alkali undergo hydrolysis to produce the acid. So when you are using acid, the acid is directly formed. However, when you are using the alkali medium, then obviously over here the carboxylate ion will be formed, okay, with the release of the ammonia. However, on further acidification, the acid molecule will be obtained. Here are some examples in which this is a multi-step example in which we are using propene under the influence of N-bromosuccinamide. The allylic position is being brominated over here under the influence of light, and then the bromine undergoes a nucleophilic attack or nucleophilic substitution by attack through the cyanide, and then the bromine is replaced and CN enters, which can be again under aqueous alkali medium can be hydrolyzed and the carboxylate ion can be produced. Herein, lithium aluminum hydride is treated with the acid, so it will undergo reduction, and on reduction it forms the alcohol, which under the influence of PbR3 will replace the OH, and a Br will come in place of OH. Now this can be replaced by the cyanide via nucleophilic substitution reaction, and so the carbon length can be increased by introduction of the CN, which on hydrolysis will again give you the acid. In another example, the same target can be achieved by using SOCl2, which on heat forms the acid chloride. This is your acid chloride, which again here the Cl can be removed from this compound by using KCN, and we have RCOCN, which undergoes hydrolysis to form the acid. This can be reduced by Clementian reagent, and the CO unit can be reduced to, so it is over here this CO unit that is reduced to CH2 to give you the acid. Again, for the cleavage of alkenes can also produce acids. So herein we are showing that this bond will be cleaved and this carbon will become acid and this carbon also will become acid. So here we are using oxidative ozonolysis wherein we are getting two different type of acids because here the R is different from this R. All I'm trying to say this R is not equal to R prime. Similarly, a similar product will be obtained when we are using KMnO4 in presence of alkali. Heat is required, or KMnO4 in presence of acid. When heat is there, these two different acids will be formed by the cleavage of, again, this bond. Hydrolysis of trihalogen compounds. So each time this OH reacts, we can think that the X is being replaced. So sequentially all the X's will be replaced and we will have the carbon joined to 3OH, which we can think is undergoing loss of water, just the way I'm showing. And at the same time, here this goes away and here the CO double bond is formed. So just like we can think here this unit like a geminal diol, and we know geminal diol forms CO bonds. So here also we can think like a geminal diol, the water is getting lost and a CO bond is formed, and so we can have the acid. We have discussed this previously. I'm just taking the names over here. We can use aldehydes with Tollens reagent, Fehling solution, or a Benedict solution, or a Sif reagent, and we can convert all the aldehydes to acids. If you have a ketomethyl group, something like this, these will undergo haloform reactions in presence of NaOH or X2. X can be here Br, Cl, or I. We can change the alkali to potassium hydroxide, same reaction will take place, or we can use slick lime with X2, or we can even use CaOCl in aqueous medium, that is bleaching powder in aqueous medium, and also which can oxidize this carbon to carboxylate. This carbon will be converted to carboxylate, leading to the formation of CX3. Okay. The next reaction is the Koch reaction, in which CO will be joined to one of the terminal carbons over here and will be further oxidized to carboxylic acid in presence of phosphoric acid at a temperature of 300 to 400 degrees centigrade. Geminal diacids can be decarboxylated on heating, and that will lead to the formation of a compound which only retains one of the carboxylic groups. So if this is getting decarboxylated, then this one is retained, okay, and CH2 will get joined to one of the hydrogens, so leading to the formation of acetic acid. These things we have covered previously in previous lectures. However, the new topic that we can see over here is the homologation of carboxylic acid. Homologation means increasing the carbon chain by 1. Herein we are reacting first the acid with SOCl2, which leads to the formation of acid chloride, which is then reacted with diazomethane, which is CH2N2. So let us have a look at the mechanism. SOCl2 heat will give you acid chloride, which undergoes nucleophilic addition substitution reaction, in which Cl will be removed and CH2N2 will be joined. We know that N2 are very good leaving group, since this particular hydrogen is joined to nitrogen carrying a positive charge, so this will be behaving as a comparatively acidic hydrogen. And once you use a base like silver oxide, so this hydrogen will be taken up by this oxide, and here N2 being a good leaving group will go out as nitrogen gas. So here nitrogen gas is going away, and at the same time R makes a migration. R is making a migration from the carbon where N2 is being left, and it leads to the formation of a ketene. Now ketene, they can undergo attack by water, obviously on this particular carbon which I have marked with an asterisk sign, because this is the electrophilic center. Followed by this mechanism, we will get the acid, and we can see on comparison that here this acid is having, with this acid and this acid, you see there is one increase of carbon CH2 group. So that is what it means when we say homologation of the acid. Some more ketene reactions. Again, if you change the nucleophile from water to alcohol, you will get an ester. You change it to ammonia, you get an amide. And if you change it to secondary amine, then obviously you get a tertiary amide. Here are some problems we have given over here. So obviously the answers will be something like this. We will have increase of one carbon CH2 group over here. You can apply the same logic down here. AE over here means Arndt Eistert synthesis. So this is giving you this. Acetic acid will go to its higher homologue, and obviously that is propanoic acid. Salicylic acid will get converted to something like this, okay, and so on. All right, here nothing will happen to this particular chiral center. Its stereochemistry will remain the same. All right, and only thing that will happen is a insertion of CH2 followed by this. So suppose if this is, say this is, what is this, 1 2 3, if we do the RS notation of absolute configuration, then we will say this is going that way. So this is basically R. All right, this is R. Similarly, this is also 1, this is 2, and this is 3. So this is also R. So R, if it is R in the beginning, then it will remain R as in the product. Some other reactions of carboxylic acids which we have classified over here. If you treat with the sodium bicarbonate, then it's simple acid-base reaction where bicarbonate reaction, then here it will be forming an acid salt. Some carbon dioxide will go away, leading to the formation of a water. These things we are studying from the elementary level. Okay, if you react it with metallic sodium, obviously this proton will be getting reduced, leading to formation of hydrogen. So half molecule of hydrogen will be formed per molecule of acid. Okay, if it reacts with the base, obviously it will form a sodium salt of the acid. Okay, so that is sodium carboxylate. Again, an acid-base reaction with RMGX. Okay, R is a strong nucleophile and also a strong base. It will react with acidic protons. Okay, and that would lead to the formation of alkanes. Okay, next, derivatives of carboxylic acids, which are obviously acid chlorides, esters, amides, can be synthesized. Now in the first reaction, okay, I'm give it in order. Suppose this is the reaction 1. All we can say that PX3 or PX5, which is phosphorus trihalide or a phosphorus penta halide, can be used to convert it into a acid chloride. Even thionyl chloride such as SOCl2 can be used to make ROCl. However, if the question is coming should we use a PX3, PX5 or SOCl2 to make an acid chloride? Then obviously it is better to use acid chloride because all the products over here under heating condition will be gas and we will be left with only the molecule. So there is no need of other separation techniques to remove things like phosphorus acid, okay, or POCl3. Now here in catalytic amount of H2SO4, a alcohol will be reacting with the acid. There will be removal of water, okay, by the acid, and then we can have an ester. Similarly, if you react this with ammonia, there also you can think water is being removed and we can have what is known as a primary amide. Okay, so when N is attached to only one carbon and the rest is NH2, it will be called as a primary amide. However, if you react a secondary amine with the acid, then N here is joined to two carbons, that is R prime and C, so it is called a secondary amide. However, when the acid is now treated with P2O5, P2O5 is a drying agent, so it takes away water molecules from two such acid molecules, leading to the formation of, so here also water is being removed from two such acid molecules, leading to the formation of acid anhydride. This is the best way of making carboxylic acid anhydrides. Okay. Now here we are discussing nucleophilic acyl substitution reactions. So here the nucleophile will be attacking the carbon which is having the plus sign because this is the electrophilic center. Then the carbon gets converted to sp3 tetrahedral intermediate, wherein the minus charge on the oxygen will come back and Y will go as a leaving group, and that is how the nucleophilic addition substitution reaction or elimination reaction takes place, replacing Y with a new nucleophile Nu. Now here Y can be many molecules or atoms such as Cl, OCOR, OR, NH2, NHR, NR2, okay, indicating chlorine. When it is there, it is acid chloride. When this is there, it is ester. This is, sorry, anhydride. When this is there, it is an ester. When this is there, it is amide. For this one, it is secondary amide, and this one it is tertiary amide. Now, if one has to ask how fast this will react, okay, with water, that is hydrolysis. So here the rate of hydrolysis will depend which group among these are better leaving groups. Now as we can see, the leaving group ability is dependent on which is a weak base. For anything to be a weak base, it has to be a conjugate base of a strong acid. So here Cl will be the strongest because it comes from HCl, followed by OCOR, followed by OR, followed by NH2, followed by NHR, and at the last we will have NR2. Now which means that for hydrolysis reaction, acid chlorides will be reacting faster than anhydrides, which will react faster than the esters, and esters will be reacting faster than the amides. Now this reaction is called Hunsdiecker reaction, which is basically a reaction of an acid with the silver oxide forming silver carboxylate salts, which under the influence of Br2 in an organic solvent like CCl4 via radical mechanism will form RBr, and CO2 will be lost, and AgBr as a precipitate will be formed. In the mechanism, as we can see, silver oxide is reacting, or silver hydroxide is reacting with the acid, simple acid base reaction leading to the formation of silver carboxylate, where the O will be making an attack, nucleophilic attack on the bromine, taking another bromine out as Br minus. Now this particular compound will undergo a homolytic cleavage, okay, under the influence of light, and a radical species, something like this, will be formed, from which CO2 will be liberated, leading to the formation of a R dot, okay, and here Br dot and R dot will be combining, Br dot and R dot will be combining and leading to the formation of RBr. The rate of the reaction obviously depends on what particular halogen we are using. So it will be faster for chlorine, a little slower for bromine, and slowest for iodine. Now here are some examples which we can do easily. All we got to do is take out the carbon dioxide and add a Br. Simply here also take out the carbon dioxide and just add Br. Okay. So these are the next two examples I'm leaving for you to do. However, this will not go the reaction as you think it will. It will not form this product. Okay, rather it will form an ester. Okay, something you can check. Okay, but this one is going to form this product. All right. The next one is called Hell-Vollard-Zielinski reaction or HVZ reaction, in which aliphatic carboxylic acids react with Br2 and Cl2. They will react with Br2 and Cl2, but they will not react with I2 and F2. Okay. Fluorine, normally we do not do fluorination directly because that leads to an explosive reaction. And I2 because Ci bonds are very weak in nature, so it is reversible. So we do not get high yields. So in presence of small amount of red phosphorus, which is important, they exclusively give monohalogenated acids. Okay. The reaction is only given by aliphatic acids that have a alpha hydrogen. So this is the most important part. Okay, if there is no alpha hydrogen here, okay, so such acids will never react. So suppose I give you acid like this, or this will not undergo HVZ reaction. Okay. Now another important point, that the halogen does not come from the catalyst. So there is no Br incorporation. It is the Cl that will join. It is the Cl that will join this particular carbon. So this is another important point that needs to be understood. PBr3 is not kept in lab, but rather it forms in C2. When red phosphorus reacts with bromine, it forms PBr3. Now this particular PBr3, as the mechanism shows, will be replacing the OH group, and here will be a RCH2OBr, okay, with the formation of POBr and HBr. Now the hydrogens are needed for the enolization. As we can see over here, it is forming an enol. That is why we need the hydrogens, otherwise the enolization does not take place, so the reaction does not take place. Now once the enol is formed, which will further, the double bond will further react via this particular carbon to the Br. So the alpha CH gets brominated, which then further reacts with another acid molecule to form, okay, alpha bromo acids, and regenerating this molecule again. Here the reaction also is possible for anhydrides, malonic esters, and also nitro compounds, which again importantly, why they are reacting? Because they can enolize. Okay. Now what is the utility of this particular compound? The Br can be easily replaced by a nucleophile like Cn. So we can have something like this, and this can be further hydrolyzed to give you a diacid. Okay, that is the utility of this compound. or you can make alpha amino acids. Or if you react these with base, then we can have alpha hydroxy carboxylates. Okay. The extension of a HVZ reaction is a Reformatsky reaction. It is almost very similar to a Grignard reaction. However, here we do not use Mg but a Zn. So we have Zn which will be getting incorporated over here, forming, as I will show you over here in the mechanism, this particular Zn will come here and leads to the formation of a nucleophilic carbon over here. Okay. So now this nucleophilic carbon is almost like an RMGX, okay, which is making an attack to the ketone, and eventually it leads to the formation of, alright, missing this, beta. If this is alpha, this is beta. So we have beta hydroxy esters. Now, why we are not using Mg in place of Zn? Because magnesium, once it forms Grignard reagent, it can self-react with this ester molecules, and so will hinder the reaction, and we will not achieve what we want to achieve. So here are some examples. So obviously this is the minus. So here we can just do one of the examples just to explain what I'm trying to say. This is your thing. Obviously here we will have ZnBr, means this is the minus. We have created the nucleophile, and that is obviously, sorry, CO2et. And now we can think just like we have studied in Grignard reactions. We will make a nucleophilic attack here, and that opens up. Okay, so technically we will have CH, alright, which is joined to a CO2et, alright. Now this is joined to, suppose, a R, that is your H, and that is your OZnBr. Now all you got to think now is, if we do a mild acidic workup, okay, this is just using, say, suppose NH4Cl. So this will form this thing, that CO2et. So that is your answer. Okay. Now one thing, as I was saying, this is linked to the HVZ. Why? To make the alpha bromo esters, acids, okay, or nitro compounds, you do need a HVZ reaction. Now, once you use these are the reagents, then you are using Reformatsky reaction. So whenever you are given exams, so keep in mind that HVZ reaction and Reformatsky reaction, they will be clubbed together and asked. They will be asking you a question. Okay. Now, here we are doing the synthesis of acyl. I have shown it before that you can use SOCl2, PCl3, PCl5. However, the side products are a little different. Here you have both. If you're using heat, then both are the gases, and that's why it is the best reagent. However, I was telling you before that for a PCl3, you can be asked how many molecules of acid chlorides are formed. So obviously 3. Okay, using 3. And here the side products are, this is phosphorus acid rather, and this is your HCl. And for PCl5, you will have POCl3 formed as a side product and HCl, and 1 molecule of acid chloride will be formed. We've just given the mechanism for the SOCl2, wherein the CO bond is making a nucleophilic attack to the SO, and subsequently this bond opens up over here like this, and this is coming back, just like your nucleophilic substitution elimination reaction, and the Cl goes away Now here again, the Cl that left away can make an attack to the carbon. This bond opens up so that the plus charge is neutralized. All right, and such a Cl can now go and make an attack to HCl. The bond can close over here to make a double bond, and this will now act as a leaving group, leading to the formation of SO2 gas and HCl, which is also volatile, and your product is ROCl. Now here I have just arranged a list of reactions which can be undergone by acid chlorides. Now again, something that we have discussed before, but just a reminder to you, acid chlorides can undergo nucleophilic attack by RMGX if you're using only one equivalent. So it can form a ketone, but this is, if you're using another equivalent, then obviously further reaction will take place here. Okay, that opens up and leads to the formation of a, after acidic workup, 3-degree ol. However, if you want to stop the reaction cleanly at ketone, then you are going to use a softer organometallic rearrange, that is R2CuLi, again in presence of THF, followed by the acidic workup to give you ketone. A similar reagent doing the same job will be R2CD, which is organocadmium, and also you are getting the ketone. However, if you use lithium aluminum hydride, then obviously the product will be your alcohol, again followed by acidic workup. So whenever you are using an organometallic reagent or metal hydrides, then always remember to work up with the water or mild acid, okay, to kill the rest of the reagent, organometallic. However, this is Rosenbund reaction, and we know that we used quinoline in presence of sulfur to poison the catalyst, and here aldehyde is our product. However, starting from the bottom, if you're using a alcohol, then obviously ester is my product. If you're using sodium carboxylate, then again acid anhydride. This is a mixed anhydride, okay? This is a mixed anhydride. So this is one of the best procedures to make mixed anhydride. If you just add water, simple hydrolysis will take place, HCl will go away. So these are very unstable towards water. If you add, if your flask gets even moisture of water, right? Okay, or vapors of water, this will be getting converted to acids. However, with bases, they will form carboxylates. This is a enamine. Enamine. Now, enamines, they can make a nucleophilic attack to this carbon that closes in, opens up to tetrahedral intermediate, then again comes back, and that's how the Cl goes away. Then further hydrolysis. So this is a good method to make 1,3 dicarbonyl compounds. Sorry. Synthesis of 1,3 dicarbonyl compounds. Okay, let me just make this a little bit clean for you. This is your enamine. So this makes an attack that goes here, comes back, that goes outside. All right. Now here again, if you have an acid chloride with an acid, I'm using pyridine to kill off the HCl that will be formed, okay, so that the reaction can be taken forward in the forward reaction. Again, you can use a carboxylate, so also this can make an attack here. Simple again, nucleophilic addition substitution reaction, and gives you a mixed anhydride. So this is your mixed anhydride. Okay. Now we're going to discuss how to make cyclic anhydride. This is a very good topic for competitive exams. Here we have a succinic anhydride, which, because the two carboxylic groups can come forward, we can think under a little bit of temperature. Okay, rather this can give away the water molecule to form. This is succinic anhydride. Guys should remember that we had used succinic anhydride in the Friedel-Crafts acylation reaction to synthesize finally naphthalene. Again, this is phthalic acid. This is phthalic acid, and this is phthalic anhydride. All right. Here we are given two acids. One is a malic acid, another is a fumaric acid. So this is your fumaric acid. Now, for these two to form, suppose, so this is y degree centigrade, suppose. This anhydride, the question is which will form faster. Now, the acid which is uh, the diacid which is in the cis form, okay, since the spatial orientation of the OH groups are towards each other near about, so we can think that X will be occurring, this anhydride will be forming at a lower temperature X. However, if you want to convert the fumaric acid to its anhydride, then obviously because they are staying away from each other, so it will be a little bit difficult for them to do so. So hence it will require more temperature. All right. Now here is the reaction of carboxylic acid anhydrides, wherein we can see that anhydrides, as we had learned, that they are less reactive than acid chlorides, but more reactive than esters. So if you use anhydride and react with simple water, first of all, then we are getting the acid. Okay, two molecules of acid. Or if you react with the base, you will get the carboxylates. However, if you react with alcohol, then we will be getting one molecule of ester and another molecule of the acid. If you react with primary amine or say ammonia, okay, then obviously for the case of primary amine, we'll be getting the secondary amide. Along with that, this particular carboxylate salt, where the cation will be obviously the primary ammonium ion. Now for synthesis of esters, as I said, we can use catalytic amount of strong acids like sulfuric acid, and it gives a fruity smell. Okay, so if you just rub an acid with an alcohol in your hand, you will get a fruity smell of the ester. Now you can also do that with acid chloride and alcohol. I've discussed this before. The pyridine is used to kill the HCl. Okay, same thing, alcohol and anhydride gives you the one molecule of ester and along with that the acid. However, if you have a phthalic anhydride, which is interesting, here one of the units will be forming the ester and the other unit will be forming the acid. All right. Now, what is trans-esterification? Trans-esterification occurs when you have already an ester and you are reacting with a high boiling alcohol. As a result, this OR will be removed and this OR will be incorporated. Okay, all right. So this type of things, they exist in equilibrium. However, you can take the reaction in the forward direction. If you're using a high boiling alcohol, something like this, and you're forming a low boiling alcohol. So if you heat this reaction mixture, this will go away and the reaction will go in the forward direction. It will lie in the forward direction more. Otherwise, they will stay in equilibrium. This type of esterification is known as trans-esterification. Now, when a base is reacted with an ester, okay, and it leads to the formation of a sodium carboxylate salt with the release of alcohol, this process is called saponification. Okay, this technology is used for making soaps, okay, from fat. The reaction is an irreversible reaction and it is kinetically second order. Okay, so here I finish my lecture, and we'll be taking amides in the next lecture and the rest of the sections. Thank you for listening. Have a good day.